Next we have oxidation number and stop notation. So in the previous videos we studied that oxidation and reduction involves the transfer of electrons, isn't it? So oxidation, during oxidation there is losing of electrons, and during reduction there is gaining of electrons. So what we can say simply as during a redox reaction or during oxidation and reduction processes, there is transfer of electrons taking place. Now, in the case of an ionic compound or in the case of ionic species, for example, if Fe2 plus by losing one electron, if it is changing to Fe3 plus. In the case of ionic reactions or ionic species, it is very easy to find out the number of electron transferred during the reaction. From this equation, it is very much clear that during this reaction there is transfer of, or there is losing of one electron during this reaction, isn't it? So in the case of ionic reactions, it is very easy to find out the number of electron transferred. But in the case of covalent compounds, it is not easy to find the number of electrons transferred during the reaction. So here we use the concept of oxidation number. So how we can define oxidation number is, it is a charge carried by an atom in the ionic state or in the combined state. It is also known as oxidation state. So oxidation number or oxidation state, we can simply call it as, it is a charge carried by an element or by an atom in the ionic state. Sometimes it will be in the form of charged species or in the form of combined state. So simply what is it? It is a charge carried by each element, okay. Now we have certain rules for assigning the oxidation state or oxidation number. Remember, oxidation state and oxidation number both are same, and that is simply representing the charge carried by each atom or each element in the given species, whether it is charged species or ionic species or in the combined form, combined neutral form like Al2O3, then MgCl2, etc. Okay. Now the first rule is, any element in the free state or uncombined state, the oxidation state will be, or oxidation number will be always 0. For example, H2, N2, Cl2, ozone, all these are free state. Free nitrogen, free hydrogen, chlorine gas, ozone gas, then sodium, potassium, iron, carbon, phosphorus, sulfur, all these are uncombined state. It is not combined to any other element. So in the uncombined state or in the free state, the oxidation state will be always 0. So here it is 0, here it is 0. So everywhere the oxidation state will be 0. Now the second rule is, in the case, the oxidation number of or oxidation state of monoatomic ions. Monoatomic means there will be only one atom present in the formula. For example, Na plus, only sodium atom is present. So in such cases, the oxidation number will be same as its charge. So Na plus, the oxidation number is plus 1, Mg2 plus, it is plus 2, Cl minus, it is minus 1, O2 minus, it is minus 2, Al3 plus, it is plus 3. So in the case of monoatomic ions, the oxidation number or oxidation state will be same as its charge. Now the third rule is the oxidation number of hydrogen. In most of the cases, the oxidation number of hydrogen, it's plus 1, except in hydrides. In hydrides, only in hydrides the hydrogen is showing minus 1 oxidation state. In all other cases, hydrogen is having plus 1 oxidation state. Then how we can identify whether it is a hydride or not? Just check the formula of the compound. If hydrogen is coming on the extreme right of the formula, that will be a hydride. Okay, if hydrogen is coming at the extreme right of the formula, that will be a hydride, and in that compound hydrogen oxidation state will be -1. In all other compounds hydrogen will be in the +1 oxidation state. So here, for example, H2O, hydrogen is on the left hand side, not on the right, extreme right. So here hydrogen is +1, here it is +1, in HNO3 also it is +1, but in LiH hydrogen is coming on the right hand side, so it will be -1. It is lithium hydride only. MgH2 also hydrogen, the oxidation state or oxidation number will be -1. Now the fourth rule is the common oxidation state of oxygen is -2. In most of the compounds, oxygen is exhibiting -2 oxidation state or oxidation number, except in peroxides. In peroxides, it will be -1. For example, H2O2. Now, only with fluorine, oxygen can exhibit positive oxidation state. Common oxidation state is -2. Then only in peroxides it can exhibit -1 oxidation state. Now only with fluorine oxygen can exhibit positive oxidation state. The reason is fluorine is the most electronegative element in the periodic table. So when oxygen combines with fluorine, oxygen will be coming only at the left hand side and fluorine will go to right hand side. So here, for example, in OF2, the oxidation state of oxygen is +2, and in O2F2 it is +1, and how it is we will see later. Now the fifth rule is the oxidation state of group 1 elements. Which are the group 1 elements? Sodium, potassium, rubidium, cesium, francium. The last member, that is francium, it is a radioactive element. So all other metals, they are having +1 oxidation state. Now group 2 elements will be having +2 oxidation state. Halogens will be always having -1 oxidation state. Which are the halogens? Fluorine, chlorine, bromine, iodine and astatine. Which are the group 2 elements? Beryllium, magnesium, calcium, strontium, barium and radium. So group 2 elements, what is the common oxidation state? It is +2. Now fluorine will always exhibit -1 oxidation state. There is no positive oxidation state or no other possible oxidation state for fluorine, because it is the most electronegative element in the periodic table. Now sixth rule is, in the case of a neutral compound, means if there is no overall charge written in the given compound, such compounds are known as neutral compounds. In neutral compounds, the sum of oxidation state of all the atoms or all the elements present will be equal to 0. For example, if in AlCl3, the sum of oxidation state of aluminum and 3 chlorine atoms should be equal to 0. Okay. Now, the next rule is, if the given species, if it is a charged species like a complex ion, or complex ions are also known as radicals. So in the case of complex ions or radicals, the sum of oxidation number or oxidation state of all the atoms present should be equal to the charge of that ion. So for example, in CO3 2-, the overall charge given is -2. So here the sum of oxidation state of carbon and the 3 oxygen atoms should be equal to -2. So in the case of complex ions, the sum of oxidation state should be equal to the charge. So these are the rules for assigning the oxidation state, or these are the few things we should remember before we assign the oxidation number of each atom. We are always assigning the oxidation state of each atom or each element present in the given compound. So we will do few questions. The question is to find out to find to assign the oxidation number of the underlined elements. So in every compound one element is underlined, we have to find its oxidation state. So the first compound given is NaH2PO4. Okay, so here it is given as a neutral compound, so the sum should be equal to 0. Now first what we need to do is those elements which we know the oxidation state, that we can write first. So here in NaH2PO4 we know the oxidation state of sodium, it is +1, hydrogen +1, oxygen -2, that also we know. Only thing is we need to find out the oxidation state of phosphorus. So let it be X. How we can find out X from this? The sum should be equal to 0. So how we can write it as, here we have only one sodium, so +1 into 1 plus hydrogen oxidation state is +1 and we have 2 hydrogen atoms, so +1 into 2 plus X is the oxidation state of phosphorus, so X into 1 phosphorus we have, so X into 1 plus oxygen we have -2 oxidation state and we have 4 oxygen atoms, so -2 into 4 it will be, and that should be equal to 0. So 1 plus 2 plus X plus -8 equal to 0. So X will be equal to 8 minus 3, that is equal to, so what is the oxidation state of phosphorus we are getting here? It is +5. So this is the way to find out the oxidation state of the underlined element. If the given species, if it is a neutral species, the sum should be equal to 0. Now in the second compound, it is NaHSO4. First we need to write the oxidation state of elements that we know. Yes, here also we know sodium it is +1, hydrogen also +1, sulfur we can take it as X, oxygen it is -2. So how we can write it as +1 into 1, we have only one sodium, plus hydrogen also we have only one, so +1 into 1 plus X into 1 plus -2 into 4 should be equal to 0. That means 1 plus X minus 8 equal to 0. So X equal to 8 minus 2, that is equal to +6. So here the oxidation state of sulfur, what we are getting is +6. Now in H4P2O7, hydrogen we know it is +1, phosphorus we can take it as X, oxygen we know it is -2. So how we can write it as +1 into 4, because we have 4 hydrogen atoms, plus X into 2, because we have 2 phosphorus atoms present here, then -2 into 7 equal to 0. So 4 plus 2x minus 14 equal to 0, that is 2x equal to 14 minus 4, that is 2x equal to 10. So x equal to 5. So what is the oxidation state? So always remember, we are always assigning the oxidation state of each atom or each element present. So what is the oxidation state of this phosphorus, the single phosphorus present here? We are writing the oxidation state of phosphorus only, one phosphorus, so it is +5. What we are getting is +5. Similarly, in the case of Na2S2O7, so here we know sodium is +1, sulfur we can take it as X, oxygen -2. So how we can write it as plus 1 into 2 plus x into 2 plus minus 2 into 7 equal to 0, because it is a neutral species, sum should be equal to 0. So 2 plus 2x plus minus 14 equal to 0. So 2x equal to 14 minus 2, that is equal to 12. So x equal to, so what we are getting here is sulfur oxidation state, what we are getting here is plus 6. So what is the oxidation state of sulfur atom here? Plus 6. Now the next one is K2MnO4 and the underlined element is manganese. How we can find? We know potassium, it is a group 1 element, so it is plus 1. Oxygen is always minus 2 except in peroxides. So here how we can write plus 1 into 2, because we have 2 potassium, plus manganese we can take it as x, we have only 1 manganese, so x into 1 plus minus 2 into 4 equal to 0. So 2 plus x minus 8 equal to 0. So x equal to 8 minus 2, that is plus 6. So in K2MnO4, manganese is in plus 6 oxidation state. So how we can write it as plus 6. Now the next one is K2Cr2O7 and the underlined element is chromium. So we know potassium is a group 1 element, so potassium is plus 1, oxygen we know it is minus 2, chromium we can take it as x. So plus 1 into 2 plus x into 2 plus minus 2 into 7 equal to 0. So 2 plus 2x minus 14 equal to 0. So 2x equal to 14 minus 2. So x equal to 12. So x equal to plus 6. So what is the oxidation state of chromium we are getting? Plus 6. Now all these are the examples where neutral species are given. So the sum of oxidation state of each element present should be equal to 0. Now we will see few charged species. For example, CO3 2 minus and the underlined element is carbon. So here we know here the minus 2 is not actually the oxidation state of oxygen, it is the overall oxidation state. The sum is actually minus 2. Now carbon we need to find out the oxidation state. We know oxygen it is minus 2. This minus 2 is the overall charge and this minus 2 is actually the oxidation state of oxygen. So let the carbon oxidation state, let it be x. So how we can write x into 1 plus minus 2 into 3 equal to what should be right? Equal to minus 2, because the overall charge here is minus 2. The sum should be equal to the overall charge in the case of radicals or complex ions. So here x plus minus 6 equal to minus 2. So x equal to minus 2 plus 6. So x equal to plus 4. So what is the oxidation state of carbon we are getting here as plus 4. Now the next one is ClO4 minus and the question is to find the oxidation state of chlorine here. So let X be the oxidation state of chlorine and here the minus means it is minus 1 and minus 1 is actually the oxidation overall charge of the species and we know oxygen it is minus 2. So here the sum should be equal to minus 1. So how we can write x into 1 plus minus 2 into 4 equal to minus 1. So x minus 8 equal to minus 1. So x equal to minus 1 plus 8. So x equal to plus 7. So oxidation state of chlorine here is plus 7. Then NO3 minus, and the underlined element is nitrogen. So let nitrogen oxidation state be X. Oxygen we know it is minus 2. The sum should be equal to minus 1. So X into 1 plus minus 2 into 3 equal to minus 1. So X minus 6 equal to minus 1. So X equal to minus 1 plus 6. Oxidation state of nitrogen is plus 5. So this is the way how should we find the oxidation number of each element present in the given compound. One more example, FeCN 6 times 4 minus. So here the underlined element is iron, let it be X. Cyanide ion we know it is minus 1, the sum should be equal to minus 4. So how we can write it as X into 1 plus minus 1 into 6 equal to minus 4. So X minus 6 equal to minus 4. So X equal to minus 4 plus 6, that is equal to plus 2. So the oxidation state of iron in this complex is plus 2. So this is about how to assign the oxidation state of each element or each atom present in the given compound, whether it is a neutral species or whether it is a complex ion or radical. Now next we have stock notation. Stock notation. In stock notation how we are representing is the oxidation number we used to represent as Roman numerals after the symbol of the metal in the molecular formula. So here we will be writing the molecular formula itself only molecular formula we are writing. In the molecular formula, after the symbol of the metal, we will be writing its oxidation state as Roman numerals inside single bracket. That is a way of representing stock notation. So for a few examples are given here. AuCl, we know it is a neutral species. So chlorine we know it is minus 1. Sum should be equal to 0. So definitely gold should be plus 1. Then only it will become 0. Sum should be equal to 0. So how we can write it as it is? The stock notation is Au. What is the oxidation? Which is the metal present here? Gold is the metal. Write the oxidation state of the metal using Roman numerals inside the single bracket. So Au1Cl. This is actually the stock notation. Now, the second one is SnCl2. Sn is stannous chloride. Here also a neutral compound is given. So, sum should be 0. Chlorine we know it is minus 1. Minus 1 into 2, it is minus 2. Isn't it? So, every time no need to write x and you no need to calculate like the first formulas. Now you can simply calculate within the molecular formula itself. So chlorine we know it is minus 1, minus 1 into 2, minus 2. Sum should be equal to 0, that means tin will be plus 2 because there is only one tin present. So how we can write the formula as stock notation? Tin, there is a metal present here, write the oxidation number as Roman numeral, that is tin 2Cl2. That is the stock notation. Now the next one is Tl2O. We know oxygen oxidation state is minus 2. Sum should be equal to 0. So here it should be plus 2. Isn't it? Thallium, here it should be plus 2, then plus 2 minus plus 2 plus minus 2, it will be 0. But here we have 2 thallium atoms. So 1 thallium it will be plus 1. So just check whether we are getting 0 or not. Plus 1 into 2 plus 2 plus 2 plus minus 2 0. So how we can write the formula as TL2. We are writing the molecular formula itself. Only after the symbol of the metal we need to write the oxidation state. O. TL2 1O. Next we have FeO. Again a neutral species. Sum should be equal to 0. Oxygen we know -2. So iron, only one iron we have. So definitely it should be +2. So how we can write Fe2O. Now the next one is Fe2O3. So oxygen is -2, -2 into 3, -6. So here it should be +6. On the left hand side it should be +6. Otherwise it won't become 0. So how it will become +6? Here we have 2 iron atoms. So 1 iron it should be +3. So +3 into 2 +6. -2 into 3 -6. +6 -6 it should be 0. So how we can write it as? Write the formula according to the molecular formula, that is Fe2. What is oxidation state? 3, that we need to write as Roman numeral O3. Next is copper. Oxygen is -2. So here it should be +2. So Cu2O. Next oxygen -2. -2 into 2 -4. So here we have only one manganese. So it should be +4. So how we can write the formula as manganese 4O2. Write the formula as such. Molecular formula should be same as such. Oxygen -2. So here only one oxygen and one manganese. So here it should be +2. Manganese 2. So this is about the stock notation, how to represent the formula using stock notation. So we are everywhere we are writing the same molecular formula. The only thing is we are writing the oxidation state of the metal. Single metal atom inside as Roman numeral inside the single bracket. Now last we have how to write the molecular formula of the following compounds. This you have already studied in 9th standard. From smaller classes onwards you are studying how to write the molecular formula by transposing the valencies. So here we will be writing the stock notation also. So first it is given as mercury 2 chloride. So what is this 2 representing? That is the oxidation state of mercury. From the formula given it is clear the elements present. So first we need to write the elements present, that is one is mercury and the other one is chlorine. Now write the valency. Mercury, the oxidation state it is given as +2. So the valency is 2. Chlorine, we know the charge or oxidation state is -1. So the valency is 1. So just transpose it. What you are getting the formula as HgCl2. So how we can write the stock notation as Hg2Cl2. Okay, just write the oxidation state after the symbol of the metal. Now the next one is nickel 2 sulfate. So here the ions or the atoms present are, one is nickel and the other one is a radical, that is SO4. Nickel oxidation state is given 2 means it is +2, so the valency will be 2. Just remove the charge from oxidation state, you will get the valency. Sulfate SO4, we know the charge is -2, so the valency is 2. Once you transpose, what you are getting here is Ni2SO4 twice, and when we write this simple whole number ratio, it is NiSO4. So how we can write the stock notation is Ni, nickel oxidation state is +2, SO4. Now the next one is thallium 1 sulfate. So the elements present are, one is thallium, the other one is sulfate of the radical. Thallium, it is given as 1, so it is plus 1 or the valency is 1. Sulfate, we know it is minus 2, so the valency is 2. So when you transpose, what we are getting here is TlSO4, Tl2SO4. So how we can write the stock notation? Tl2SO4. Write the same molecular formula and write the oxidation state using Roman numeral after the symbol of the metal. Next we have tin 4 oxide. So elements present are tin. Tin formula is Sn, and the oxide, so oxygen is present. Then here it is given as 4. So oxygen, we know it is minus 2, so the valency is 2. On transposing, what we are getting here is Sn2O4, and if we write the simple whole number ratio, it will be SnO2. So the stock notation will be Sn4O2. Next is iron 3 sulfate. So we have iron and the radical sulfate. Iron oxidation state is given 3, so the valency is 3. Oxidation state is plus 3, so valency, just remove the charge, so 3. Sulfate, we know the charge is minus 2, so the valency will be 2. So what we are getting here is Fe2SO4 thrice, isn't it? So the stock notation will be Fe2, oxidation state is 3, then SO4 thrice. And the last one is chromium and oxygen. Chromium oxidation state is given, that is plus 3, so the valency is 3. Oxygen, we know it is minus 2, so the valency will be 2. On transposing, we are getting, so the stock notation will be Cr2 3. So this is about how to write the stock notation of different compounds. So from the Roman numeral written inside the single bracket, we can identify the oxidation state of the metal ion or metal atom. So only remember, we are writing the molecular formula itself. If it is Cr2O3, we are writing Cr2O3 only. Same formula only we are writing. The only thing is, we need to write the oxidation state of this metal atom inside the single bracket using Roman numerals.